Example 2. Evaluate the integral of the natural log of x dx. Solution. Here we don't have much choice for u and dv. Let u equal the natural log of x, then du equals 1 over x dx, and dv equals dx, and v equals x. Sidebar. It's customary to write the integral of 1x dx as the integral of dx. Check the answer by differentiating it. Back to the text. Integrating by parts, we get the integral of the natural log of x dx equals x, the natural log of x minus the integral of x dx over x, which equals x, the natural log of x minus the integral of dx, equals x times the natural log of x minus x plus big C. Integration by parts is effective in this example because the derivative of the function f of x equals the natural log of x is simpler than f. Example 3. Find the integral of t squared e to the power t dt. Solution. Notice that t squared becomes simpler when differentiated. Open, whereas e to the power t is unchanged when differentiated or integrated. So we choose u equals t squared, then du equals 2t dt, and dv equals e to the power t dt, where v equals e to the power t. Integration by parts gives equation 3. The integral of t squared times e to the power t dt equals t squared e to the power t minus 2, the integral t e to the power t dt. The integral that we obtained, the integral t e to the power t dt, is simpler than the original integral, but is not obvious. Therefore, we use integration by parts a second time, this time with u equals t and dv equals e to the power t dt. Then du equals dt, v equals e to the power t, and the integral t e to the power t dt equals t e to the power t minus the integral e to the power t dt equals t e to the power t minus e to the power t plus big C. Putting this in equation 3, we get the integral of t squared e to the power t dt equals t squared e to the power t minus 2, the integral of t e to the power t dt equals t squared e to the power t minus 2 open t e to the power t minus e to the power t plus c plus big C closed equals t squared e to the power t minus 2t e to the power t plus 2e to the power t plus big C sub 1, where big C sub 1 equals negative 2 big C. Example 4, evaluate the integral e to the power x sine x dx. Sidebar, an easier method using complex numbers is given in exercise 50 in appendix H. Example 4, evaluate the integral e to the power x sine x dx. Solution. Neither e to the power x nor sine x becomes simpler when differentiated, but we try choosing u equals e to the power x and dv equals sine x dx anyway. Then du equals e to the power x dx and v equals negative sine x. So integration by parts gives equation 4. The integral e to the power x sine x dx equals negative e to the power x cosine x plus the integral e to the power x cosine x dx. The integral that we have obtained, the integral e to the power x cosine x dx, is no simpler than the original one, but at least it's no more difficult. Having had success in the preceding example, integrating by parts twice, we persevere and integrate by parts again. This time we use u equals e to the power x and dv equals cosine x dx. Then du equals e to the power x dx, v equals sine x, and equation 5, the integral of e to the x cosine x dx equals e to the power x sine x minus the integral e to the power x sine x dx. At first glance, it appears as if we have accomplished nothing, because we have arrived at the integral of e to the power x x sine x dx, which is where we started. However, if we put the expression for the integral of e to the power x cosine x dx from equation 5 into equation 4, we get the integral of e to the power x sine x dx equals negative e to the power x cosine x plus e to the power x sine x minus the integral of e to the power x sine x dx. Sidebar. Figure 1 illustrates example 4 by showing the graphs of f of x equals e to the power x sine x and big F of x equals 1/2 e to the power x open sine x minus cosine x close. As a visual check on our work, notice that f of x equals 0 when big F has a maximum or minimum. Figure 1, graph F and graph big F. Back to the text. This can be regarded as an equation to be solved for the unknown integral. Adding the integral e to the power x sine x dx to both sides, we obtain the integral e to the power x sine x dx equals negative e to the power x cosine x plus e to the power x sine x. Dividing by 2 and adding the constant of integration, we get the integral of e to the power x sine x dx equals 1/2 e to the power x open sine x minus cosine x close plus big C. If we combine the formula for integration by parts with part 2 of the fundamental theorem of calculus, we can evaluate definite integrals by parts, evaluating both sides of formula 1 between a and b, assuming f prime and g prime are continuous, and using the fundamental theorem we obtain equation 6. The integral from a to b of f of x g prime of x dx equals f of x g of x from on the interval from a to b minus the integral of a to b g of x f prime of x dx. Example 5. Calculate the integral from 0 to 1 of tangent, the inverse tangent x dx. Solution: let u equal the inverse tangent of x, then du equals dx over 1 plus x squared, dv equals dx, and v equals x. So formula 6 gives the integral from 0 to 1 tangent, the inverse tangent of x dx equals x, the inverse tangent of x on the interval from 0 to 1 minus the integral from 0 to 1 x over 1 plus x squared dx equals 1 plus the inverse tangent of 1, or the inverse tangent 1 minus 0 times the inverse tangent 0 minus the integral from 0 to 1 x over 1 plus x squared dx equals pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. To evaluate this example, we use the substitution t equals 1 plus x squared. Since u has another meaning in this example, then dt equals 2x dx. So x dx equals 1/2 dt when x equals 0, t equals 1 when x equals 1, t equals 2. So the integral from 0 to 1 x over 1 plus x squared dx equals 1/2 the integral from 1 to 2 dt over t equals 1/2 the natural log of the absolute value of t from the interval on the interval 1 to 2 equals open equals 1/2 open the natural log of 2 minus the natural log of 1 close equals 1/2 the natural log of 2. Therefore, the integral from 0 to 1, the inverse tangent x dx equals pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx equals pi over 4 minus the natural log of 2 over 2. Since the inverse tangent x is greater than or equal to x for x greater than or equal to 0, the integral in example 5 can be interpreted as the area of the region shown in figure 2. See figure 2. The graph of y equals the inverse tangent of x.